Hierarchical clustering is kind of a bread and butter technique when it comes to visualizing high dimensional or multidimensional data. It's very simple to use. The ideas are fairly intuitive for most people, and it kind of can serve as a really quick way to get a sense of what's going on in a very high dimensional data set. So, of course, like most clustering techniques, for example, like k-means, for example, the basic issue that you have to deal with when you define the method is how do we define when things are close together and when things are far apart? Because all clustering methods, in some sense, try to tell you when one thing is closer to another thing versus something else. And so, for example, things that are in a cluster are closer to each other than they are to elements of another cluster. And so we have to define what it means to be close, what it means to group things together, how do we group things together. And then once we have a distance notion, and we have a way of grouping things together, how do we visualize the processing that we've done, the calculation that we've done, and how do we interpret how the grouping is put together. Cluster analysis is a really important and widely used technique. If you just type cluster analysis into Google, there are literally millions of results that come back, and it's a widely applied method in many different areas of science and other applications. And so it's useful to know kind of how some of these techniques work. So hierarchical clustering, as is denoted by the title, involves organizing your data into a kind of hierarchy. And a common approach is what's called an agglomerative approach. And the idea, which is kind of a bottom-up approach. So you start with the data as kind of individual data points, and you start lumping them together into clusters until eventually you have your entire data set is just one big cluster. So you can imagine there's all these little particles floating around, and eventually you start kind of grouping them together into little balls, and then the balls get grouped up into bigger balls, and then the bigger balls get grouped together into one big massive cluster. And so that's the kind of agglomerative approach to hierarchical clustering, and that's what we're going to talk about here. And so the basic idea is that you got to find the 2 points in your data set that are the closest together, and then you kind of merge them together to create one super point. So the merged point is not an actual point in your data set, but you can think of it as being a new point. And then you kind of remove the original 2 data points and you substitute with that kind of merged point. And then you kind of repeat this over and over again. So then you find the next 2 closest things, and then you put them together. And then once you've kind of put things together, you get like a little tree that you can show that shows the ordering in which things were put together. And so this approach requires 2 important things. One is a distance metric. So what does it mean? How do you calculate the distance between 2 points? And the other thing that is required is an approach for merging points. So once you've figured out, okay, well, these 2 points are the closest, how do you merge them together? And so the nice thing that hierarchical clustering produces is a tree, which is sometimes called a dendrogram, that shows how things were merged together. And so arguably the most important question to kind of resolve in a hierarchical clustering approach is to define what do we mean by close. Because if you have a definition that doesn't make sense for your problem, then you just get garbage in, garbage out, right? So if you have a distance metric that doesn't make sense, then the results that you get will be relatively meaningless. So there are a few examples of distance metrics that are used out there. Probably the most kind of familiar distance metric is the Euclidean distance, which is just kind of the straight line distance between any 2 points. A kind of analogous distance metric is the correlation between 2 points, or the correlation similarity. And then another metric is the binary distance, or the Manhattan distance, and I'll talk a little bit about what that means in a second. So you have to pick a distance metric that makes sense for your problem, so that you can produce results that also make sense. And so here's Euclidean distance, a simple diagram. So if you take 2 cities, for example, Baltimore and D.C., or Washington D.C., then if you put them on a map, for example, and so you can imagine that the center of each city has an x and a y coordinate, and you want to say map the distance between the 2 centers of the 2 cities. Well, you can draw a straight diagonal line between the 2 cities, and then you can calculate the distance kind of in the usual way. And the distance is going to be a function of the difference in the x coordinates and the difference in the y coordinates. So to calculate the Euclidean distance, you take the difference, in the x-coordinates, you square it. You take the difference in the y-coordinates and you square it. You add the two squares together, you take the square root. That's the classical definition of Euclidean distance. So you can imagine, in real life, it would be like if a bird were to fly from DC to Baltimore, they would just fly straight from one city to another. They could, because they can fly in the air, and they're not impeded by things like roads or mountains or whatever. And so that's the straight line distance between the two cities. Whether that makes sense for you depends on whether you're a bird or something else. And so you have to think about kind of that in the context of your problem. Now, Euclidean distance is easily generalizable to higher dimensions. But even if you have, instead of here we just have 2 dimensions, but if you have 100 dimensions, you can easily take the difference between 100 each of the dimensions, square it, sum together, and then take the square root. So it's a very nice kind of, it extends very naturally to very high dimensional problems. The Manhattan distance gets its name from the idea that you can look at points on a kind of a grid or a city block grid. Imagine you're in the city of Manhattan in New York, and you want to get from one point to another. So you can look at the 2 black circles on this diagram, and if you want to get from one point to another, if you're in a city, in a city block, you can't just go directly from one point to another because there'll be all these buildings in the way, right? You'd have to follow the streets. And the streets, because they're in a grid, you can either go up or down or left or right. The green line here, in that case, would represent the Euclidean distance, which would be like, if you were a bird and you want to fly over everything across the 2 points. But as a person walking on the ground, you have to take either the red line, the blue line, or the yellow line, or any other kind of pattern in between. The point is that you'd have to travel along the city blocks. And so the distance that you would travel along the city blocks here in the gray, you can imagine the gray lines as the streets, that's the Manhattan distance, and it can be written formulaically as the absolute sum of all the different coordinates. So if you have 2 coordinates, then you sum the distance that you travel in the x dimension, and you sum, and then the absolute value of the distance you travel in the y direction. And so the Manhattan distance can be useful in some contexts, and so because it may in some contexts more accurately represent the distance between 2 points. In particular, in a city like Manhattan, 2 points may be very far apart, even if they seem relatively close, in a Euclidean distance sense.